Okay, let's now start 8.8 to 8.9. And so today we're going to talk about the oxidation of alkenes and then addition of carbenes to alkenes. All right, so first, let's talk about oxidation of alkenes. So a very popular reaction that you're going to see is the cleavage to a carbonyl compound. And so if you remember that carbonyl compounds are compounds that have a carbon that's double bonded to an oxygen. And of course, this carbon can be attached to any R groups. And so this part right here is the carbonyl. And so what we're seeing is an alkene creating a carbonyl, but it's through cleavage. So let's look at mechanism. So we have carbon 1 and 2. And so the reagent is going to be ozone. And notice it's under cold conditions in a solvent. And so what you're going to see is your ozone molecule is going to interact with your carbons. And so you're going to create this intermediate initially, which is molinozonide. And this is an important intermediate to just take note of. I often see that in exams and assessments and standardizing. So this molinozide, it goes through a rearrangement type of mechanism reaction. And so after it rearranges, you'll see that it creates an ozonide. And so after this ozonide is created, what you're going to have is now zinc coming in as a second step to actually completely cleave and create two carbonyl groups. And so through these steps, what you're seeing is carbon 1 and carbon 2 being cleaved. And so what I like to draw to be able to see this, let's say this is carbon 1 and carbon 2. This alkene is cleaved. So carbon 1 and carbon 2 are no longer there. And so in its place, so they're broken apart, you're going to have two carbonyl groups. And these are two separate compounds. All right, so let's go to the next slide. All right, so here we're able to see the reaction and the actual two products that are formed, not just a general reaction, but see it actually in place. So let's take a look at this. All right, so in the first example, you can see that we have our double bond right here in between our ring and our carbon. And so again, this is ozone, oxidation using ozone with the cleavage, right? And so you have your first step and your second step. So we know it's going to go all the way to the carbonyl compounds being produced. And so if I cleave right in between here, and then I add my oxygens in between those two cleavage points, if you will. And of course, we saw the mechanism, so that's not exactly, it's not just like cutting it and adding them. That's not how it works. However, to be able to get to your products, that would get you there. And so you can kind of see that this is that carbon here, and this is that carbon here with this carbonyl group here, which is this, and then the carbonyl group here, which is this part of it. Now, notice that this carbon right here has two methyl groups on them. So after it cleaves, you want to make sure you have those still there. So again, so simple. Cut off, oxygen, oxygen, done, rewrite it. So now let's look here. We have our double bond here. And so if I was to count my carbons, I have the 1 here, and then my 7 CH2s, and then I have my 9th carbon there, because 1, 6, 7, 8, all the way to 8. I mean, 1, 2, 3, 4, 5, 6, 7, 8, and then the 9th one there. And then on this side, I have a carbon here, 7 CH2s again, and then 9 that has a carbonyl group already on it, and then it's an ester. And so again, I cleave it here, creates a carbonyl group, and then on this side a carbonyl group. Now notice, because with this cleavage, you have hydrogens on those carbons. So in this case, instead of creating a ketone, you created aldehydes. Okay. Now ultimately this is considered an ester, which is why it ends in noate. But the carbonyl that was created, notice that is an aldehyde. Okay. And this is also an aldehyde. All right, so now we're going to talk about oxidizing reagents other than ozone, which can cause double bond cleavage. Okay, so we saw that ozone can do it, but also potassium permanganate can produce carboxylic acids and carbon dioxide if hydrogens are present on the carbon double bond carbon. So the main point is if hydrogens are present. So here you see your carbonyl group and it's on the N. So you have a CH2 here and then you have your CH there with your double bond. And so what's going to happen is this is going to cleave. And so on one side, you're going to get carboxylic acid in this case, which is the side that has all of the other portions of it. But because it's a CH2, it's going to be completely oxidized and turn into carbon dioxide. So if you have an terminal alkene, it's going to completely oxidize and form carbon dioxide. All right, so I like calling this reaction Haya because it cuts the diol, if you will, and creates two carbonyl groups, or it can actually create two ketones. So let's look at this. And we see what I call Haya multiple times. Now with it, it's actually a periodic acid. And so pretty much alkenes can be cleaved by hydroxylation to create a diol, and then from there it can react with your periodic acid to create cleavage, which creates your two carbonyl groups. So let's take one step back. That is not being shown. Let's say this is a double bond. And then let's say this is we create a diol with this. Remember we have this reagent here. All right. And then from there, you get your diol. Once you have your diol, don't forget your CH3. There's a CH3 here. Once you have your diol, CH3 looks a little funny. All right. Once you have a diol, you now can treat it with this reagent in the presence of water and THF. And what's going to happen is the carbons that are 1,2-diol, they're going to cleave. And when those cleave, those carbons are going to have carbonyl groups on them when they're getting their oxygens from here, from the reagent. Okay? But ultimately, it does cleave. And so let's look at this version of cleavage. So this time, the cleavage is in a ring. And so even though it cleaved, these compounds are still connected to each other from 1 to 6. So you still get only one molecule. Whereas in this case, these carbons are only connected by this one link. And since it's only by there, when this cleaves, they're completely separated. And so this and this become carbonyl groups, if you will. This hydrogen's gone. Carbonyl groups. You know. And of course, your bond angles have to be corrected, but you get 2 of these. Okay. Now, if the diols are not symmetrical, let's say I have, let's see, how can I do this? And something kind of like this. This would still cleave, but now I would get 2 different products because I have my carbonyl group there, but then I have 1, 2, 3, 4 with my carbonyl group there. Okay. And so with those cleavages, you just want to pay attention to which carbons are there and which ones are being cleaved. All right, so the worked example, what products will be expected from the reaction of 1-methylcyclohexene with aqueous acetic acid? So let's just practice drawing this structure. So we have cyclohexane with 1 methyl group on the one. All right, and we're going to treat this with potassium permanganate in an aqueous solution. So let's go to the answer. So in this reaction, let me move my lovely drawing that I did. Uh-oh, I went too far. Give me a second, and I'll back up. All right. So if you notice, with here, there's no terminal alkene. And since there's no terminal alkene, what's going to happen is simply this is going to cleave. Now the side that has no hydrogens is going to be a ketone. However, this side has one hydrogen on it, and so it's going to oxidize and form a carboxylic acid. Okay, so no hydrogens, ketone. One hydrogen, carboxylic acid. Two hydrogens, carbon dioxide. All right, so this is the second reaction that we're going to do for this lecture, and it's the addition of carbenes to alkenes. And so carbenes, as you can see here, is a carbon with two or with a set of lone pairs, and then two R groups attached to it. Okay, this is a carbene. So, alkene additions is a reaction with a carbene to yield a cyclopropane. Adding asymmetrically across double bonds to form cyclopropanes. Okay, so if you can see, what you're going to have is creating this cyclopropane with there. So let's kind of look at it a little deeper. So mechanism. So base abstracts the hydrogen from chloroform, okay? Leaving behind an electron pair from the CH bond and forming a trichloromethanide anion. All right, so we have a base come in, take this hydrogen off, and you're left with this. Once you have this, what's going to happen is you're going to have a loss of a chlorine ion, and that's going to create a neutral dichlorocarbene, okay? A neutral dichlorocarbene. So once this is initiated, this is going to happen naturally so that we can have a neutral. So it's trying to get into its neutral state because chlorine is electronegative, and so it's good just carrying the negative charge compared to carbon carrying a negative charge. All right, so then with we're looking at the valence electrons. You can kind of look at the differences with dichlorocarbene. You have, this is an sp2 carbon. And so while it does have some lone pairs, you still have a vacant p orbital available. And this is similar to carbocations, where you have a vacant p orbital available. Okay, so we're just looking at those different, or similarities, I should say. All right, so addition of dichlorocarbene with cis-2 pentene is stereospecific. And so we got to make sure we understand that. So we're going to have this trichloromethane here, and treating it with carbon dioxide is going to create that carbene that we just talked about. And then when that carbene is corrected, you now have these orbitals available to create this structure here. Now, what they want to point out is that it's stereospecific, meaning that it's going to be connected and added on the same side in the same planes of each other, causing the hydrogens that are on that alkene or whatever substituents are on that alkene to be both pushed and be cis to each other. And it's going to be based, let me make sure point this out. It's going to be based off of the stereochemistry of the starting material. All right, so this is called Simon-Smith reaction. This is a method for preparing non-halogenated cyclopropanes. This does not involve a free carbene, okay? We don't have a free carbene. However, it does have a carbenoid, okay? So reaction of diiodomethane with zinc copper allo produces zinc iodide. And so we're going to first create this zinc iodide carbenoid, all right? So from there, what's going to happen is you're going to take these two reagents, they're going to form this carbenoid, and that's going to satisfy or stabilize this carbene. But remember, it's not a free carbene, all right? It's being stabilized by a carbenoid. Once that happens, the alkene can now react with the carbene to create that cyclopropene that we've been seeing. And this is the Simon-Smith reaction. So it's a little different than the other ones because we're going to be using a non-free carbene. All right, so what will be the product of this reaction? All right, so the Simon-Smith reaction. You find your double bond, and you know that double bond is going to create a what? Cyclopropene. So let's go ahead and see how we do it. Plain and simple, where your double bond was, it now has this, what we gonna call it? A tri membrane. Then we have like what we say, four, yeah, I guess we say tri. Membrane, member ring, sorry, member ring. All right. So that should be straightforward. It's not too difficult. You just have to remember the reagent portions of it. But if you understand this part and the preparation, you'll know to look for this diiodomethane, and then you'll see your zinc alloy, which creates your non-free carbene, which can go through the rest of the reaction. Now, it's important to show, because it's not showing me whether it's cis or trans in this structure, that two different isomers can be formed because it's based on the stereochemistry of the double bond, as I mentioned before. And so in this case, you can have two stereo isomers. Guess what? That's it for this section. Let's go ahead and take a break before we start our next part and our final part for chapter 8.